Next up, we have Boltzmann distributions and kinetic energy distribution curves. First, though, little notes about the absolute temperature scale. So if you ever see that term absolute temperature, it means the Kelvin temperature scale. Notes that 1 degree Celsius is equivalent to 1 Kelvin, meaning the difference between, say, corresponding Celsius temperatures and the difference between difference between Celsius temperatures and their corresponding Kelvin temperatures are the same. So these scales are just shifted. And so they are shifted by 273. So to convert from Celsius to Kelvin, we'll take the Celsius temperature at 273, and that'll give us our temperature in Kelvin. This will be important for some calculations that we do later on. So maybe highlight this, make a note of this, keep this handy so you can remember later on. We usually measure things in science in Celsius. However, the Kelvin temperature is the SI unit of temperature, or the Kelvin unit, I should say. And the Kelvin temperature scale is based on molecular motion. So the lowest possible temperature ever, lowest theoretical temperature is absolute zero, it's called 0 Kelvin. And at absolute zero, there is no particle motion. So again, this is the lowest temperature. Nothing can drop below this. Absolute zero does not mean 0 Celsius. There are temperatures way below 0 Celsius. In fact, what is absolute zero in Kelvin? Sorry, what is absolute Celsius? I can't talk today. What is absolute zero in Celsius? Go ahead and pause the video and give me that number. So you have 0 Kelvin. If we solve for Celsius, we have to subtract 273 from that. And so absolute zero in Celsius is negative 273 Celsius. Notice that if you double the Kelvin temperature, you will double molecular motion. So very important, this relationship between temperature and molecular motion. We'll talk about it throughout this unit and even next. Take a look on page 384 in your textbooks. We see a graph showing exactly what we just wrote here. So doubling the temperature, say from 100 Kelvin to 200 Kelvin, doubles the amount of kinetic energy of the particles. Doubling from 200 to 400, though 400 is not shown on there, also doubles the kinetic energy. Now, only doubling the Kelvin temperature doubles the kinetic energy, though we do see a relationship there between Celsius and Kelvin. All right, letter C. Thinking about the definition of temperature. Temperature, if you recall, is a measure of the average kinetic energies of the particles in an object. And we saw that on the animation that some of the particles were moving faster than others. So it says here, at a given temperature, all the particles present move at a variety of different speeds. And so we're going to show that graphically. And this is known as a Boltzmann distribution. So let's go ahead and set up our axes. So on the y-axis, we're going to label that as number of particles. So imagine you have some substance. It could be any state of matter, but we usually focus on gases, but it doesn't have to be. So y-axis, the number of particles versus speed. So be careful with this graph and the next one I'm going to show you. So number of particles versus speed. So let's take a look at some substance at some temperature. The distribution of the speeds of the particles looks something like this. So let's say that this is the distribution of the particles in some substance at 20 degrees Celsius. That's a degree Celsius. Let's see if we can make, there we go, 20 degrees Celsius. So what do we see? Let's take a look at some of the points along this curve. So let's say, how do we interpret this point here? Very few particles, so we have a relatively low number of particles, have a very low speed, are moving at a very low speed. If we pick something over here, again, we have very small number of particles, if we go all the way to the left, are moving at a really high speed. How about right here? We have a lot of particles moving at some intermediate or in between fast and slow speed. All right, so let's try this. Let's take this substance and heat it up. If you take this substance and heat it up, what effect will that have on the particles themselves? We saw this in the animation. If you increase the temperature, it's going to cause the particles to move faster. So at a higher temperature, on average, the particles will be moving faster. Question is, how do we show this on this graph? So let's draw a second curve for this same substance, but at a higher temperature. What does that curve look like compared to this one? How can we show that at a higher temperature, more particles are moving faster than at the lower temperature? Go ahead and pause and think about that. All right, so let's go ahead and add our second curve. I'm going to show it in a different color. Now, before I draw this second curve, something to keep in mind. If we were to calculate the area under the curve, you can do that using calculus. So you'll get there soon if you're not there already. If we calculated the area under the curve, we would get on this graph the total number of particles. So here's what you need to be careful of when drawing these graphs. If you take the same substance and heat it up, well, when we draw that second curve, it needs to have the same size as this first curve. So let me show you what that could look like. Now you might be thinking, no, that red curve is smaller than the blue curve. No, not smaller. Yeah, it's shorter, but notice that it's also wider. And so try to show as best as you can that the curves are the same size. They just have different shapes. So let's say the red curve represents the substance at 50 degrees Celsius. Well, what do you notice? That curve is shifted to the right is how I like to explain that. So at a higher temperature, more particles have a higher speed or are moving at a higher speed. And so we need to shift that over to the right. Let's add one more. Let's take the same substance at, I don't know, 0 degrees Celsius. What is true about the particles on average at 0 degrees Celsius compared to the particles at 20 or 50 degrees Celsius? Go ahead and answer that question. At 0 degrees Celsius, a greater number of particles will be moving slower than at 20 or 50 degrees Celsius. So how do we show that? How do we show that on this graph? Again, let's add a third curve. How do we show that there are, on average, more particles that are traveling at a lower speed? So this time, we're going to say the curve is shifted over to the left. So let's label that. That green curve shows that there's a large number of particles that have a low speed and not a lot of particles that have a high speed. So again, very, very, very important, the relationship between temperature and molecular motion. The higher the temperature, the higher the average speed of the particles. Before we go to page 383, let's move on to letter E. We'll go back to 383 in just a minute because there's something else I want to show you with the Boltzmann distribution. All right, next up, kinetic energy distribution curve. Set up our axes. Once again, on the y-axis, we have number of particles. Any guesses what goes on the x-axis? You guessed it, kinetic energy, right? Kinetic energy distribution curve. So if at a certain temperature, the particles are moving at a variety of speeds, that then implies that the particles have different kinetic energies. Remember, the formula for calculating the kinetic energy is 1/2 mv squared. So if we're talking about a particular substance where mass is constant, then if there's a different temperature, if we have a certain temperature, there's a certain average kinetic energy. The particles are moving at a variety of speeds. And so again, we get a variety of kinetic energies. So let's take a look at what that looks like. So let's say this represents the curve distribution of the kinetic energies of the particles. Again, notice there's a direct relationship between velocity and kinetic energy. As the velocity of the particles increases, so does kinetic energy, and the opposite is also true. So that's why these curves look the same. So let's take this same substance and heat it up. If you increase the temperature, it's going to cause the particles to move faster. If the particles are moving faster, then the kinetic energy will also be higher. So be careful. We got showing two different but related things. Temperature versus velocity, basically, and temperature versus kinetic energy. Increased temperature, that increases average kinetic energy. If you increase the kinetic energy, that means the particles will be moving faster. Now, if you have room, let's go back to the Boltzmann distribution. I want to show you something different on this graph. All right, this time instead of comparing the same substance at different temperatures, we're going to look at different substances at the same temperature. So let's say you have, I don't know, 3 gases. And I'm going to do different ones than what's shown in the book. So let's say we have helium. Let's go with argon. No, we'll just go noble gases, make it easy. Helium, neon, and argon. All right, so we want to look at, and then something else at, let's go 20 degrees Celsius. So at 20 degrees Celsius, what is the distribution of their speeds of the particles? So I'm going to start, let's do this. I'm going to draw the curves, and then you tell me which is which. Try to match kind of the same colors as I did before, not that it matters. All right, so we have 3 curves here. One of them represents the distribution of speeds of the helium atoms. One is for neon, and one is for argon. Now, notice that all 3 of these gases are at the same temperature. So that means they have the same average kinetic energy. Well, what is different about helium, neon, and argon? They have different masses. So as we talked about a couple lessons ago, if you have different substances that have different masses, they will have different velocities if they have the same amount of kinetic energy. Do you remember the relationship between mass and velocity? If so, let's label these curves. Let's start with the green curve. So notice, what do you notice? On average, these particles are moving the slowest, right? Slowest speed. So which of these gases would the atoms be moving the slowest? Is it the lightest or the heaviest? Heavier particles move slower than lighter particles when at the same temperature. We talked about this already. Now we're just showing it graphically. How about the red? On average, the particles have the highest speeds. They're moving the fastest. So in which gas would the particles be moving the fastest at 20 degrees Celsius? That would be the lightest ones, or helium. And then neon's mass is in between argon and helium. So the neon atoms will be moving at speeds in between, on average, speeds in between argon and helium. So again, we've got a lot of graphs. They look the same. Make sure you know how to explain what's happening as shown on each of these graphs. We learned a little bit about solids earlier in the year, so let's dive in a little deeper. Some general characteristics. Particles of a solid are held in place by strong interparticle forces. Attractive forces. We talked about this as well the other day. What makes a solid is that the particles are held together very tightly. by some attractive force. This could be dispersion forces. This could be dipole-dipole forces. This could be hydrogen bonding. This could be covalent bonds. This could be metallic bonds. This could be ionic bonds. Those are all attractive forces. And so only the strongest attractive forces will hold the particles together and end up with a substance that is a solid. Nevertheless, even though that the particles are held tightly together, they do move a little bit. So the word we use to describe the motion of the particles in a solid is vibration. So they vibrate along their bonds. Before we get to these vocabulary terms, let me give you some other terms. Not melting point, but just how about melting? In the margin, write the definition of melting. What does that mean if a substance melts? Go ahead and pause the video. Melting is a physical change. It involves a change from solid to liquid. So what is melting point? Melting point is the temperature at which a solid melts, the temperature at which a solid turns into a liquid. Again, in the margin, go ahead and write the definition for freezing. Pause now. Freezing is also a physical change, a phase change we call it, which involves a liquid turning into a solid. So freezing is the opposite of melting. Freezing point is the temperature at which a substance freezes, or the temperature at which a liquid turns into a solid. What is the melting point of ice? Ice melts at 0 degrees Celsius. What is the freezing point of water? Water freezes at 0 degrees Celsius. Notice anything? So melting and freezing point of a substance occur at the same temperature. Talked about this before. Solids are dense. In fact, a substance exists in its most dense state of matter, usually as a solid. This is not true of water, of course, but most substances are the most dense as a solid. Because the particles are touching each other, solids are not compressible. We talked about this with gases. So you cannot very easily make a solid have a smaller volume. And again, because the particles are held tightly together, solids do not flow, nor do they fit the shape of their container. They're able to maintain their own shape. When the particles of a solid are arranged in a highly organized way, they are known as crystals or crystalline solids. We can see that just below in the next section, crystalline solids. There are 4 types of crystalline solids. I'm going to go into a little bit more detail than what's in the notes here, so make sure you add that. They are called ionic, molecular, metallic, and covalent network solids. Let's start with ionic. Ionic solids consist of particles held together by strong electrostatic forces, it says here. This term electrostatic refers to the force of attraction between oppositely charged particles, aka we're talking about ionic bonds. So an ionic solid consists of particles held together by ionic bonds. Ionic bonds are very strong. And because of that, ionic solids possess very high melting points. Example, sodium chloride is an ionic solid. It's made up of sodium ions and chloride ions all held together by ionic bonds. You don't need to know this number, but the melting point of sodium chloride is 801 degrees Celsius. If you were to pour some sodium chloride in a pan and put it on your stove and turn it on, would the salt melt? No way. Your stove does not get hot enough to melt any ionic solid like sodium chloride. Go ahead and pause the video and list some other ionic solids, maybe substances that I've used in the lab. Pause now. What have we used in the lab? We use Copper 2 chloride in the chemical reactions lab. We've used copper 2 sulfates. Not that we use it in a lab. Calcium chloride, potassium iodide. These are all ionic solids. All right, molecular solids. Molecular solids, in a molecular solid, the particles are held together by some type of intermolecular forces. Sometimes collectively intermolecular forces are known as van der Waals forces. So we're talking dispersion, dipole-dipole, or hydrogen bonds. Now, are intermolecular forces strong or weak attractive forces? Well, it says here they are weak, which is why molecular solids have certain properties such as low melting points. So speaking of those intermolecular forces, dispersion forces, remember their strengths vary quite a bit. They increase when a molecular atom becomes longer and more massive. Technically, it's not really has to do with mass, but has a larger electron cloud. The larger the electron cloud in an atom or molecule, the more polarizable it is, the stronger its dispersion forces. Remember, dispersion forces occur between all polar and nonpolar molecules. Force of attraction in molecular solids could be dipole-dipole forces. Of course, this occurs between opposite ends of polar molecules. Could also exhibit hydrogen bonding. This occurs between separate molecules where both of the molecules contain nitrogen-hydrogen or oxygen-hydrogen or fluorine-hydrogen bonds. All right, so what are some examples of a solid where the particles are held together by either dispersion forces, dipole-dipole forces, or hydrogen bonding? How about that one? Can water be a solid? Of course, we call it ice. Does water have a low melting point? I would say 0 degrees Celsius is pretty low, so yes. So in this case, the particles are held together by hydrogen bonds. Here's another one. Can carbon dioxide be a solid? Sure can. What is it called when it's a solid? Yep, dry ice. Very low melting point. So that is a molecular solid. Here's another one. That's the chemical formula for sucrose or table sugar. If you were to put some sugar in a pan and put it on your stove and turn it on, would that sugar melt? Sure would. It's a molecular solid, relatively low melting point. Third type in the notes here, metallic solids. Metallic solids consist of particles that are held together by metallic bonds. So usually we're talking about metal atoms held to other metal atoms. We're talking about metals. Metallic bonding occurs when the valence electrons on the metal atoms become delocalized. And the individual metal cations are then held together by something called an electron sea. Let me show you an example of what that looks like, and then I'll give you examples of metallic solids. Something like this, you have a whole bunch of cations, and there's these electrons, the valence electrons of the metal atoms that are delocalized. These electrons are able to move around. This is why metals are good conductors of electricity. They have these electrons that are able to move between different atoms. All right, so what are some examples of metallic solids? Well, any metal. Iron, gold, sodium, silver, tungsten. These are all metallic solids. Last type, known as covalent network solids. I know your notes say something different, and that's fine. Network solids or macromolecular solids. In a covalent network solid, all of the particles, all of the atoms are held together by covalent bonds. Covalent bonds are the strongest type of attractive force between particles. So that means covalent network solids have extremely high melting points and are very hard. We're talking about some of the hardest substances on Earth. Now, there are lots of examples, but here are the ones you need to know for this class. The most commonly remembered or known is diamond. A diamond is made up of all carbon atoms, all covalently bonded to each other, makes for a very hard object, very high melting point. Another one is quartz or silicon dioxide. Again, silicon and oxygen atoms this time, all held together by covalent bonds. This one is often used in abrasives and cutting tools, silicon carbide. If you've heard of the term carbide bits or carbide blades, it's usually this substance. Or it could be this substance, tungsten carbide. Actually, my ring that I always wear is made of tungsten carbide. It is really, really, really hard. All right, on page 405 is a summary of the types of crystalline solids, the attractive forces between them, melting points, and some examples. So go ahead and take a look there. All right, so I'm going to pause the video here and then I'll continue with liquids in the next video.